MIT Aeroastro department. I'm also have an appointment at Draper Laboratory, which is across the street. I'd like to thank my collaborators, Professor Hoffman, Professor Weiss, and Professor Hewitt, as you'll notice, who are all from different departments around MIT, both from engineering and from the sciences. So this talk is going to be about two platforms, and by platforms I mean vehicles that we've been thinking about that will enable lunar surface science. So currently, we've had orbiters, sedentary landers, and rovers to explore other planets. So orbiters are really good at giving global coverage, but they're usually far removed from the surface. So you get resolution issues, and you're not there to do in situ science. Sedentary landers provide you that in situ science, but you're only able to do things within arm's reach or to the horizon that you can see. And rovers go a step beyond that and allow you to do in situ science in a local neighborhood where you can drive around for the lifetime of the rover and go to multiple locations on the surface. The two platforms that we're talking about, or that I'd like to talk about today, add an extra bit or simplify something that we've had before. So hoppers are a vehicle that take the lander and essentially use it to propulsively go to another location. So they provide regional exploration. You can still go to multiple locations, and it also gives you the opportunity to precisely go places on the moon that are hard to reach either by rovers or by trying to land a single lander the first time down. They also allow you the ability to do a rapid traverse across the surface, which enables certain types of science. Penetrators, and when I'm talking about penetrators, I mean hard landers, things that can take thousands to 10,000 G landings and survive, are spacecraft that we're looking at that are simpler landing systems that don't require a lot of delta V, that don't require a lot of propulsion, a lot of guidance, navigation, and control, which embed themselves in the surface but still have all the avionics, electronics, and payloads survive, so you can do things like network science or nodal science on the moon. So first I'll talk about hopping in a little bit more detail. What is hopping? So hopping takes that lander platform. It's the same sensors, the same actuators that have landed on the surface once, and essentially all you have to do is add more fuel and be able to restart your actuators. And you lift off the surface, you accelerate in a direction, you coast, you brake, and then you descend on another spot. So now you're able to do arm's reach science over a larger region. So you can land and do science at multiple locations. You can do science along the way when you're traversing. So one of the aspects that we've developed for hoppers is a fixed attitude, fixed altitude hop. So something that traverses with a fixed platform so that you can do imaging along the way, spectroscopy along the way, and provide a stable platform for those sensors. And also the ability to do vertical science, which is not something that we've been able to do in the past very easily, the ability to scale cliffs and crater walls, and I'll get into some more examples in a slide or two. One of the interesting concepts that I want to talk about a little bit more is the ability to land precisely, very precisely, anywhere. So when we talk about lunar landing, these in the past 5 years, we've talked about landing within 100 meters of a location on the surface. With the capability to land multiple times, you can actually land very coarsely the first time. Apollo landed on the order of 1 kilometer from where it wanted to be. The Apollo landers did. And then hop from one location to another location and get very close to within meters of a location that you desire to be. So this is the analogy that I use. It's kind of like golf. You can try and shoot a hole in one from orbit, and you might get close. Or you can just try and hit your way there closer and closer with each successive hop. Some of the comparisons that I wanted to make was, for example, the Mars rovers, this number might be a little bit outdated by now, have traveled about on the order of, I'd say, 15 kilometers in the past 5 years or the 6 years that they've been operating, whereas a hopper can do, on the same amount of mass, 20 kilometers on the order of 5 hops, which is something that can be done in a matter of seconds or minutes. So you can traverse a large region much quicker and gain science in a much more rapid fashion. You can also now do vertical science, so scaling cliffs. So you can hop to the bottom of a cliff face, ascend across that cliff face, maintain a fixed distance from that cliff face, take imagery, spectroscopy, and understand the stratigraphy that lies along the path. And also you can fly over hazardous regions and land very precisely inside a hazardous region. So if you come near a rock field, which for some rovers might be very hard to traverse, you would actually be able to hop over that field, assess what rocks are there, do some path planning, and then go back and land in the middle of that rock field in a place that might be more interesting. So some of the things that enable hoppers are a totally propulsive vehicle. So the more propellant you have on board, the more capability you have to go places. So something that enables you to be able to go more places is having very small sensors on board to do the science that's desired. So for example, this is one of the things being developed at Draper Laboratory. This is the Lattice spectrometer, which has been talked about here. It's a very small, very low mass, low power, high performing spectrometer that can be carried on board a small vehicle like a hopper and can be used for science on the way as we travel across the surface. Switching gears a little bit to penetrators. So when I talk about penetrators, we're talking about things that couple with the surface but are able to survive, and the electronics are able to survive, and the payloads are able to survive. And these kinds of vehicles enable doing network science in a more cost-effective way. So they have much lower delta V requirements. Some of them have no delta V requirements. Looking at the plot that's on the bottom left, this is a plot of what it would take to drop, how much delta V it would take, or how much acceleration you would feel, or deceleration you would need to bury a penetrator 1 meter, 2 meters, or 3 meters into the surface, dropped from altitudes from 200 kilometers up, and with delta V pushes, which can be done by propulsive units or can even be done mechanically from aboard a mothership. If you look in the top right, that will allow us to hit the surface with 1,000 or about 10,000 Gs of loading and be able to survive that. So in the top right is a concept that we have where we have a mothership that's an orbiter that carries along these penetrators that don't require a lot of computation on board or propulsion on board, and essentially drops these off in orbit as it orbits the moon. These things provide direct coupling to the surface, so you can do seismometry, you can set up a network to do seismology across the surface, you can do heat flow experiments, you can place electromagnetics on board to have antennas on board, and I'll show that in one of the next slides. So one of the things that enables penetrators is being able to develop low power, low mass, impact hardened electronics and instruments. And so leveraging work from things that have been done in other fields, from the DoD applications, there's been inertial instruments that have been made that can withstand about 18,000 Gs of acceleration or deceleration. So these instruments are able to survive a very hard G load and then be able to send data back in a very small package. So what we have in the bottom left here is a small unit that's been developed and has some inertial sensors on board, some processing on board, as well as some other instruments. And this is a very small package that fits in about a 3 by 3.5 inch little block. We're MIT and Draper are developing a new type of seismometer that's also on the order of this very small size, a MEMS seismometer, which can do 10 to 5 nanog per root hertz, has 10 to 5 nanog per root hertz sensitivity that can be impact hardened for these types of missions, specifically for the seismology mission. Another concept, which this is from my advisor, my master's advisor, Jackie Hewitt, is to set up a large network of radio antennas on the surface to do cosmology and wide field array surveys on the moon. So being able to cheaply and cost effectively set down a large amount of items without having to provide propulsion for each unit would be a great benefit for enabling these types of missions. So I'd like to acknowledge some of my colleagues at Draper and MIT who I worked with on hoppers, on penetrators, on talking about the seismic instruments that we've developed. And we're hoping that in the next, hopping is something that we've been demonstrating at MIT and Draper. It's a poster that we had last year showing some of the technology that we've done. We're at the point now where we're demonstrating that on Earth, showing that hopping is a viable form of surface mobility. And penetrators are something we're hoping to develop where we can show through some of the other technologies that we have that we can throw something out of a flying vehicle, have it impact the surface, couple to the surface, and have all the instruments survive on board and take that to the next level for TRL. So if there's any questions, I'd be happy to take them. Thanks.
It's about your penetrators. I mean, I was curious to say you said they were low mass. I mean, typically the problem with penetrators isn't making the electronics survive. It's the fact you've got no atmosphere, so each one has to be a 3-axis stabilized spacecraft to make sure they go in the right way, and also to try and do precise targeting. I mean, other space agencies have spent lots of money and found out that it's very, very hard. So I was a little surprised by kind of a throwaway comment, or we just chuck them off the spacecraft and they'll land. How much have you done an actual design for the penetrator themselves? Because like I said, each one is a mini 3-axis stabilized spacecraft.
Yeah, and I see where you're coming from. So for example, for things on atmospheric bodies like the Earth, it's a lot easier to do that stabilization. And you're right, when you go to a place that's an atmosphereless body, you have to be able to stabilize that spacecraft. But it doesn't necessarily need a propulsive unit on board. A lot of the cost and mass and complexity that comes with these types of things is providing that propulsive unit. You can do the spin stabilization with other types of units on board. And when you're talking about precision, these types of penetrators probably won't provide high levels of precision on the surface, but they will provide the capability to have many of these across the surface.
For hoppers, at what level of TRL are you at the moment?
We're very close to I'd say we're at about 5. We're very close to 6. So what we've been trying to do at Draper and MIT is develop a platform that actually demonstrates hopping in a relevant G environment. So we've built a test bed that allows us to take out lunar gravity or take out Earth gravity and use cold gas thrusters to mimic lunar gravity and fly our vehicle around the lab, demonstrating this capability to do a fixed attitude, fixed altitude hop.
What is the importance while doing the hopping of the coast phase, sort of skimming the lunar surface, as opposed to a more parabolic trajectory?
That's a very good question. So there's some operational issues with doing a ballistic hop. So ballistic hops you use a higher thrust to weight to essentially blast off the surface. And you have to do a very tentative attitude maneuver at the top to turn your vehicle back around so that you point your main thruster back at the ground. And as you approach the ground, then you have to do another very high thrust to weight maneuver. Whereas with this, you can keep a very low thrust to weight just above 1. Essentially, you're hovering above the surface and blasting across. We've had some students in the past who've done studies on the delta V cost between a ballistic hop and what we call this hover hop. And actually, the thing that takes into account, the most delta V is taken up by actually the ascent and descent phase. And so the ascent and descent phase of each type of hop is essentially the same, because both vehicles do have to vertically rise and maintain a fixed attitude on the way up. And then a ballistic hop will turn and do a large delta V maneuver, whereas a hover hop will fire sideways thrusters and it will still have gravity losses along the way, but it's comparable to a ballistic hop.
And maybe you said it, I may have missed it, the range for the hover hop?
Sorry, the question's coming from somewhere.
What range are you looking at for the hover hop?
So the hopper has been designed for the Google Lunar X Prize. So we're looking at 500 meters to 5,000 meters. And that's just a function of propellant. So we've designed a 110 kilogram hopper that has 10 kilograms of fuel left over at landing, after first landing, that can go 500 meters on 10 kilograms of fuel.
Have you done any cost estimates on either of these concepts for an actual flight mission?
We have. So the X Prize, for the X Prize we've done costs. We've tried to fit our hopper into, I'll say, a Falcon 1E, and we've been able to have a system that has closed to provide a hopper to land on the surface and do a 500-meter hop in the size of a Falcon 1E. So then you can think about what it takes to build a lander. A lander is a simpler system than a rover, for example, because you have to build 2 systems, whereas with a lander hopper, it's the same sensors, the same actuators, and the same platform.
Yeah, I want to ask a question. With the hopper, what about the blast damage of the site? Each site is going to be sprayed a bit.
Very good question. A question that I get a lot. So a hopper can't do everything. It will contaminate depending on the propellants that you use and what you're interested in looking at. It will contaminate areas that you're trying to go to. But some of the things that are of interest are being able to look forward and see the science as you go. So before you land, if you have sensors that are forward-looking, that are vision-based or spectroscopy, you can do that. But right below your landing site, you will have contamination. Some of the things that hoppers enable that it's very hard for other vehicles to do, they do contaminate the local area. But for example, hoppers are one of the few vehicles that would be capable of hopping into the bottom of a crater, doing a survey at the bottom of the crater, and then hopping back out, being able to communicate and then survive, because the bottom of those craters can be very cold or permanently shadowed, as we saw.